Alan Matheson Turing was a renowned mathematician and logician from England who contributed a lot to the fields of maths, philosophy, computer science, artificial intelligence, etc. But the main role of his that we are going to talk about today in this video is that of the breaking of Enigma code. Enigma was a cipher machine used by the German military to communicate with each other during the Second World War. The British were not the first who decoded Enigma. In fact, the Poles had done it in the early 1930s under the guidance of Martin Rejewski. But in the likelihood of a German invasion, they passed on this crucial information to the British, who formed a secret code-breaking group called Ultra under Alan Turing. And with their help, the Allied powers were led to victory because the Germans were also in contact with the Japanese as they shared these encryption devices, and ultimately, a lot of manslaughter and destruction was avoided. The Enigma machine was used to encode strategic messages before and during the World War II. It is made up of several parts including a keyboard, a lamp board, rotor, internal electronic circuitry and the plug board. The continuously changing internal flow of electricity is what caused the rotors to change, and it's not random. It creates a polyalphabetic cipher that could be different each time it was used. The number of permutation of setting which was available to the encoders is what made Enigma so difficult to create. Combining 3 rotors from a set of 5, the rotor setting with 26 positions and a plug board with 10 pair of letters connected, the military has 159 quintillion different settings. Each time a key is pressed on Enigma machine, the rotors turn and the code changes. This means that the message AA could be encoded something like MK even though the same key was pressed twice, and no matter how many times the letter is used, it will never give back the same output. Some historians believe that cracking the Enigma was the single most important victory by the Allied power during the World War II, and it shortened the war by 2 years and saving more than 14 million lives.
So far, we have seen how the Enigma code worked and how it was nearly impeccable. But as history suggests, it did indeed have flaws, which eventually led to its undoing. And arguably, the biggest flaw with the Enigma code was that a letter could never be encoded with itself. Secondly, many messages encrypted using the Enigma code quite often had a fixed format which was repeated over and over. For example, the Germans sent a weather report any morning, which were always the same apart from the actual weather. This doesn't seem like it should matter, as even if you keep inputting the same letter, it gets encoded to a new letter each time, as discussed earlier. However, combined with the first flaw of the code, it became possible for these messages to be decrypted by some clever analysis. And lastly, the rotor settings of the Enigma machines kept at every German station were updated at the stroke of midnight each day. Basically, they tried to force out randomness, which actually turned out to be a flaw, because if you knew the rotor settings of the previous day, then you know the same settings wouldn't be present in the same location the current day. As we'll see in a minute, one of the British code breakers, Alan Turing, found a way to use these flaws to break the Enigma messages, which gave the Allied powers an edge over the Germans in World War II, and it might be among the various reasons why this presentation is in English today and not in German or Japanese.
With roughly 1.5 to 10 raised to 20 combinations, it was simply impossible for humans to find the right one. This is where the bomb comes in. It's named after a much simpler Polish code-breaking machine called the Bomba, which also tried to break the Enigma but was unsuccessful. Now, the bomb was the brainchild of British mathematician, cryptographer, and one of the first computer scientists, Alan Turing. Him, along with another mathematician and cryptographer, Gordon Welshman, designed the first bomb machine and was later constructed and installed in March 1940. In order for the bomb to solve the Enigma, you needed a thing called the crib. The crib is a hypothesized word, for example, weather report, that we think will be present in the ciphertext. So here, because we know that no word in the Enigma is mapped onto itself, we try to find the exact location of the word weather report by moving the plain text across the ciphertext. So here in the first example, T is mapped onto T, and we know this cannot be the position of the plain text. We keep moving until we find a valid combination where no letter is mapped onto itself. We repeat this process until we find all possible valid combinations, and these are called valid crypts. In the previous example, we saw how to perform crib analysis to find valid crypts. For sake of simplicity, let's say we have found the correct crib. In this example, I have the German word for weather report and its ciphertext. As you can see, we have a map between each letter. For example, W is mapped onto S, the second letter E is mapped onto N, and etc. And using this, we form a graph. From this graph, 10 such pairs would be entered into the bomb machine. In real life, this would be done using a set of wires that goes from each letter and connects to the other one. Arbitrary drum settings would be used at first, and then you start the bomb machine to check for all the combinations. Here you can see the rotors are spinning. What it's actually doing is it is going through all the combinations to find the correct one. Okay, as we can see here, it has found the ring settings, the initial position of the rotors, and the plug board settings. We can now use this and set the Enigma using these settings to solve the complete code. In the simulator example, we saw with the good crib text, we can find the initial rotor settings, ring settings, and the plug board connections. Although this does not necessarily give all the plug board connections, simple cryptographic methods can then be used to find the further connections once you have found the rotor settings. Although a real bomber would go through all the combinations in just 20 minutes, what we took for granted in this example was that we did not find the initial rotors, which has a total of 60 combinations, and we did not go through all the other potential crypts. In order to compute all this, you needed much more bomb machines, and in fact, during World War II, over 200 of them were created. The fact that the Allies had created this mechanical supercomputer and cracked Enigma was a heavily guarded secret, so much so that after the war was over, all bombs were destroyed, and the files were kept a secret up until 2010. The bomb is not just a forgotten technology, it was erased from history altogether.